Hello everyone, I am Miguel Nunez and I am super happy to be your TA in this Neuromatch Academy. I was in fact a first-gen Neuromatch Academy student and I am super happy to be here because this is an amazing opportunity to you to learn a lot of things and meet super wonderful people and to me to get experience trying to teach you and solving problems if you have any. So please um, tell me if you have any questions during the explanation. Um, so we will be talking about multilinear and multiple linear regression. As you can remember from the past lectures and tutorials, uh, we were talking about linear regression and making confidence intervals about our estimations. So in this case, we want to extend this technique to multiple inputs. You need to remember that um, linear regression perhaps could be or could seems to be like a very simple model, but in fact, uh, upon this model, a lot of models are built. So if you actually understand very good this model, you will have a lot of intuition about what is happening in a lot of other models. So you need to recall the linear regression in the case of the univariate linear regression is just a mapping between an input and an output, right? X's and Y's. In this case, as any model, we will have an error term because, as you may know, any model is perfect. In this particular case, the error term, as you might remember, has some particular properties. The first one is that this error term has zero mean, and we imposed a distribution upon this error term, which is a normal distribution uh, with some variance. So having remembered this information, we want to extend the ability of this model to actually do a mapping between multiple inputs and an output. As you may remember, um, this this we need to actually add an extra term for the bias. The bias is just an offset from the region in which we are drawing this line. So this makes the model more flexible. We can start our line from various points in the space. So in the multivariate case, we will have um, um, a number of parameters and then our inputs. We can express this using a vector notation this way, or um, usually we use the matrix form. In this case, it's just a matrix multiplication. This is useful because this matrix X is often called the design matrix. The design matrix is called the design matrix because in statistics, we can use this matrix and manipulate this matrix to do a lot of tests and try to answer a lot of questions. In this case, we will be doing basic estimations around the multiple linear regression, but you need to remember that the concept of design matrix is very important. Right. So in the design matrix, we will add the actual bias term by adding a column of ones. This will make that this column became the bias term, and then we will have our inputs in this case each feature or regressor and the number of samples that we have. So you need to remember we have multiple inputs, in this case x1 and x2, and an output, and we want to actually make a line to map the inputs and outputs. So we will be using the ordinary least squares estimator that has this form. A particular ability that you need to develop during the academy is to actually translate mathematical stuff to code. So take notes around how to translate between these two worlds, because in particular, I think that this ability is crucial to actually perform good in any coding stuff related with science. So we will proceed with the first exercise. In this case, we want to compute theta hat. As we are seeing here, we need to translate this formula to code. First of all, we need to comment this line because this line is related with a race error if we do not nothing. And then we need um, to start translating, right? So first, we want to do the inverse of the of this multiplication, this matrix multiplication. In fact, this matrix multiplication represents the covariance matrix. So we want to accede to the lineal library of NumPy and then calling imp. This represents the inverse. So we want X transpose. We want a matrix multiplication with that we need to use the add symbol and then just translate and be comfortable with that translation, right? So we have already the first part of the formula, then we follow with the next. We need to actually project this information onto the output. So y, oh sorry, I was forgetting the matrix multiplication, and then this should be working. So let's try it. Here we need to uncomment these lines, and let's see. And it seems that it's working and we did a good job, right? So we can actually measure our mean square error and plotting our predictor plane. As you can see, we are minimizing the perpendicular distance of each point to the hyperplane that is actually predicting the expected value of the output given the observations.